the figure that we want to action in the discussions.
Okay, we are very happy to have Itay from Berkeley as the assistant for dark matter.
So, hi, thank you very much for inviting me. I'm sorry I missed the original invitation, but I'm happy I'm here now. I'm going to tell you indeed about quantum magnetometry in search of dark matter. This is something I've been doing for a few years by now. I have a lot of things to talk about, but I'm very happy to skip them. I much prefer that you actually understand, and I talk to the air, so feel free to ask questions, and I will skip what needs to be skipped for us to finish in a reasonable time, but really feel free. So we're going to start with a very brief introduction on axions and axion-like particles. I'm not really going to go too much into the details of that, but if there's anything later that you felt you missed because this is a short introduction, let me know, and I can explain a few more details. Then we're going to have a very long introduction. I will explain to you how spin-based magnetometers or co-magnetometers actually work. This is going to be essentially the setup that will later be used to explain kind of several different techniques that we have used in the NASDUCK collaboration as well as before that to look for dark matter. So here I'm going to give you kind of a long introduction so you're actually able to follow this part, and we'll hopefully have time to cover some new ideas that are new both for dark matter physics and for magnetometry or metrology in general. While here these are more already established techniques, things that people have known about, just have not used to look for dark matter. And hopefully, of course, we'll finish with a summary. So, the QCD axion, what a lovely particle. It was originally postulated to solve a problem called the strong CP problem. You have this parameter theta that we've never measured, and you promote it essentially to a field, and this resolves why we would not have expected to measure it until now in very few words. And these are pseudoscalars as well as pseudo and Boole-Gulson bosons, and therefore their couplings are derivative couplings. They look kind of like this thing, and we're going to discuss these a bit more. But another important feature of axion-like particles, on QCD axions, is that their mass has a relationship to how much they couple to matter. So you see here that the coupling goes like 1 over Fa, the mass goes like 1 over Fa. That means that the lighter in mass you go, the less you expect it to couple to the standard model. And because most of this talk is going to be stuff that's very light, okay, that means it couples very weakly to the standard model, which is why QCD axions are going to be not actually that important for most of the talk. The last thing I want to mention about QCD axions is that they can be a cold dark matter component. That means they would be all around us, sitting here being non-relativistic and everything. And in my talk, essentially, throughout of it, every time we're looking for them, we're going to think they are all of dark matter. Now, the actual thing most of this talk is going to cover is axion-like particles. So these are particles that are kind of like axions, hence axion-like particles. And they don't have anything to do necessarily with this original motivation, the strong CP problem. There are many other reasons why you would expect such particles to appear. They are still going to be pseudoscalars and almost always also pseudo and Boole-Gulson bosons, so they would still have similar couplings. But this relationship is going to be broken down. Essentially, this means that when we're looking at very light axion-like particles, this no longer means that they necessarily couple so weakly to the standard model, because this relation has broken down. I'm still going to assume that they are all of dark matter, essentially, every time I look for them. So, this is the kinds of interactions that axion-like particles can have with a standard model. And by the way, when I later say the word axions, usually from context, I mean axion-like particles, and it will be very clear when I mention actual QCD axions. But the axion-like particles, the kinds of interactions they have with the standard model, there's, I think, essentially 3 main ones. There's the Primakov effect, where in the presence of a background electromagnetic field, an axion can be converted into a photon. This is what most people look for when they look for axions, and I do have works that look for that, but they are not for today. These are mostly the Snipant collaboration. This interaction, which is also quite well known, because this is what actually resolved the strong CP problem. This is kind of the original motivations for QCD axions. And this interaction couples the axions to gluons, and I have not worked on them before, but I am currently working on them, but that's also not what we're going to talk about. Instead, we're going to focus on this interaction, which couples axions to fermions. So this interaction is going to couple the spin, and we're going to spend some time talking about it. But first, I want to take you back to the before time, before COVID, late 2019. What I'm showing you here is the current constraints of the time on the interaction of axions, here with neutrons, and here with electrons. So these are the 2 parameter spaces. Of course, the lower you go, that means the weaker they couple to the standard model. And on the x-axis, we have the masses. In green or gray here, these lines are coming from terrestrial Earth-based experiments. The red lines, regions here and here, are coming from astrophysical constraints. And as you can see, this is quite sad. There's like 5 orders of magnitude between these two things, which, as a terrestrial-based person myself, makes me a bit sad. Because indeed there's a huge gap here that is only currently covered by astrophysical constraints that tend to have more systematic uncertainties associated with them, and there are also actual, theory-based models that can evade them because the environment of the star is very different from the Earth-like environment. So I think it is good if we can come up with ways to look for these interactions in an Earth-based experiment. And the way to do this, we need to understand first what is this actual interaction, and this is the Hamiltonian of that interaction, which I showed you a Lagrangian for before. And essentially what it does is it couples to the spin of a fermion. Okay, there's this field which we call the anomalous field. Okay, there are different ways to write it with a coupling constant, without it. You can write it however you want. But this is essentially the Hamiltonian of the interaction. And what's interesting about this Hamiltonian, you see here, there's the density of the axions, there's the coupling constant here, the velocity, and this coupling constant is, again, very small, right? Because otherwise you would have found them. And this effect is linear in the coupling constant. There's a slight subtlety here that I don't really want to talk about, but I felt that without putting the asterisks. But essentially it is linear in the coupling constant, while most astrophysical stuff, when we talk about production, are going to go like like amplitude squared, so that's going to look like the square of this very small number. So that's why we might be able to actually compete with these astrophysical constraints. And of course the question is, I can write whatever I want, but I can also write the logarithm of that. As long as I cannot measure it, that's not very interesting to say that something is linear. And can we actually measure it? And the hint I have for you is the Zeeman splitting, something from the regular all lovely standard model, which couples also two spins of fermions. And here we have something called the gyromagnetic ratio. It is a property of different particles. Okay, the electron has one, the neutron has one, etc. And here we have the magnetic field. And as you can see, this thing looks essentially the same from the perspective of a spin. They both couple the same way. And that's why we're going to be able to use spin-based magnetometers to look for them. Yes?
So can you explain that why linear is so special? Because as soon as you assume that dark matter is being sourced by, axions are being sourced by dark matter, most experiments then turn to linear coupling.
So direct detection experiments, the majority of them, those that look for absorption, those that look for scattering, would be actually go like the square of this. Because essentially once you exchange energy, you need to look at the matrix element squared. However, what here we're going to measure, because we're measuring a Hamiltonian, is essentially energy splitting. Energy splitting can be linear in the coupling constant. Like I said, there is an actual subtlety here about once you reach the quantum limit, you end up always going like things squared. However, currently we have not reached yet the quantum limit. There's still a lot to push forward before we reach the quantum limit. And currently, because we are measuring energy splitting rather than transition probabilities, we are going to go linearly. Is that clear?
So at the stage of writing the Hamiltonian, all experiments that assume axion will be sourced by dark matter will be linear.
True.
So then you convert this.
Are you talking about the fact that the coupling is linear in the axion field?
No. So I think whether this Hamiltonian that he's written is linearly depending on G or quadratically depending on G. So now when you convert this Hamiltonian into an observable, then maybe in some experiments you're measuring power, in others you're measuring energy splitting, and then...
You're entirely right. That's why I said here, indeed, I could also write the logarithm of this object, and that would go even slower. Exactly. Now the question is, what is the observable? And that's why we need to discuss how we measure Zeeman splitting and magnetometers, which are indeed linear in this thing.
Okay.
And again, there's still a slight subtlety here that is not really crucial right now. So this is behind you seeing an actual picture of one of the magnetometers I worked with. And now we're going to explain what spin-based magnetometry, and co-magnetometry is just when you have two of these magnetometers at the same time, or more than two, I guess. So what it means. So, to understand spin-based magnetometry, we need to talk about the fundamental equations, which are the Bloch equations, not my own, which govern how spins behave in the presence of magnetic fields as well as different other things that we're going to see in a second. So these are first-order equations. They tell us how the derivative in time of the spin changes. And the first term there's a bunch of stuff I'm going to completely forget about. You will see this asterisk again later. That means that I'm hiding some details, and for some of these I also have a backup slide with the extra details. For some of them, we're simply going to have to wait until later in the talk where I address these subtleties. But the main details are, first of all, this torque term. So this is what the Zeeman splitting does to the equations of motion. it creates an effective torque. So if I have a spin pointing that way, a magnetic field pointing that way, it will make the spin want to rotate. It's like this. So if I start out with spins all pointing in the same direction and I have a transverse magnetic field, some of the spins are going to fall down. They're going to start to rotate around. And because the Hamiltonian looks the same for the Zeeman splitting and for the anomalous fields, essentially that means that the anomalous fields will also create a torque-like term. The next term I have, is a term that decays excitation. Now, if I shake my whole system very hard, okay, what will happen is that the spins are going to be pointing in some random direction related to technical details of how well I shake them, and then the system will relax over a period of 1 over gamma. Okay, so this thing means that essentially it stabilizes the system. This is the rate of stabilization in the system. And as we will see, it has many other important effects. And the last term that we have, as I just said, the system will stabilize over phi over gamma. However, if I only have these two terms, the only stable solution for the system is S equals 0. If you wait a long enough time, the spins are not going to have any preferred direction. They're simply going to be thermally distributed. And what this term does, which there are several different ways to actually create this term. Right now it's just a math artifact. But it creates a macroscopic polarization. So essentially it gives the spins a preferred direction. We call this the pumping term. Okay? And that means that if I wait a long enough time, even if I remove all external magnetic fields, I'm just having kind of these two things, the spins are going to be polarized to a specific direction rather than all pointing in random directions. So these are our fundamental equations, and we're going to solve them. But to solve them, we're going to simplify them first. And by the way, admittedly, I'm going to soon show you the actual answer. If you're not following the full derivation, that's not too bad. The main important part would be the actual result, yes?
In that previous equation, did all the terms have the same units?
I hope so. So the gyromagnetic ratio is measured in units of hertz per Gauss, or energy per Gauss, depending on how much you like h bar to be 1. And this is measured in units of Gauss. So this is measured in units of 1 over a second times the spin. The anomalous field, because it is coming in a Hamiltonian, it would be measured in units of energy. Okay, so if you kind of cancel out the gamma, it's going to be again energy cross S, so that's fine. This is the stabilization rate, has the units of 1 over time. And this is also units of 1 over time.
Sorry, the last term looks a little weird because if I think of S as living on a sphere, if it's pointing in the z direction, that's trying to make its radius increase, so that doesn't look like it has just the last term.
Yeah, I understand. So the statement is that this term has...
I would have thought a stabilization term would have been proportional to something like S minus some direction or something.
This term, this gamma, is the sum of several terms, one of which is R.
You really put part of the stabilization term in the difference.
When you create a pumping term, you have to also cause decay.
Okay.
Because the pumping is is a destructive process. So you're entirely correct. So, as I said, we're going to now simplify our equations. These were 3D equations. We don't like 3D vectors. We like single numbers, and they're going to be complex. So, the spin in the z direction is not going to be an interesting quantity until we get to the last few slides of this talk. And essentially, that's why we're going to take it to be non-changing. And most of the spins are going to be pointing in that z direction. Most of them are pointing exactly as if they were in their steady state. Okay, we're talking about small perturbations from the steady state. So we only care about the spin in the x and y direction, and to avoid using 2D vectors, we're instead simply going to write this s perpendicular, which is the real part is coming from the x direction, imaginary part is the y direction. So whenever you see this s perpendicular, simply think the spin in either the x or y direction, depending on if it's real or imaginary. And we started out with these 3D equations, and you have to trust me that hopefully I did the pluses and minuses correctly, and this is what we're going to end up happening. You don't need to look at this equation also too much. The main important thing here is, as you can see, torque terms that make you rotate, will now have i's in front of them, because, again, real parts are x, imaginary part are y, so if I multiply a real thing by I, it's going to become imaginary. That's kind of x wanting to become y. If I multiply imaginary things by I, they're not going to become real, so that would be y wanting to become real. So that's kind of the torque. And we're already going to remove some things. We're going to remove this anomalous field in the z direction, and the z direction here is just the direction of the pumping term, of the term that, determines what the steady state is, because the only effect we're really sensitive to is transverse fields. And again, we're now going to actually solve them, and the derivation, again, is less important than the actual result, which we're going to spend some time on in a moment. This was the anomalous field. This was the equation we just derived, and we're going to do some Fourier transforming, as well as ignoring some subtleties about the fact that this cosine has both a real and a counterclockwise and a clockwise rotating component. We're going to forget about that for now, and we're going to take this BZ to be constant, and this is going to be our result. And again, this result is super important, so I have one giant slide dedicated to it. This result, we're going to use it again and again in this talk, so I'm going to explain every single term, even though we explained some of them already. So the first term we have is the transverse spin. This is the observable we have. We're going to measure it, again, until the last few slides at the top. Everything we want is encoded in this spin. And as you can see, it is indeed linear in our anomalous field. So when we measure this object in a linear way, we're going to be able to be sensitive linearly to this coupling constant. And when I say perpendicular, it is always perpendicular to the pumping direction. The pumping direction is going to be determined by whatever pumping process I choose to work with, which is usually going to be some laser that has a preferred angular momentum that my spins are going to be imparted upon. They're going to get that direction as well. So this is what we actually measure on the left-hand side. But what we care about is the things on the left-hand side, right-hand side, and specifically the signal. So this is the effect of dark matter. It would be encoded into this little small letter b perpendicular, and this is what the axion-like particle generates. It is a field in the direction of the velocity of the axion. It's proportional to the coupling constant. So this is what we actually want to know when we measure this thing. But we also have other terms here. Specifically, this is transverse magnetic fields. Transverse magnetic fields can either be from noise, whatever system you're working with, it will almost certainly have some background magnetic field, and they're going to create some noise that, is not going to be the thing you want to measure. But also, as I alluded to earlier, our magnetometers are actually co-magnetometers. So we're going to have several species of magnetometers, and they're going to affect one another, and this is also going to contribute to perpendicular magnetic fields. They're going to apply magnetic fields on one another, and this is going to be mapped into this object. It is important to note that this object is proportional to the gyromagnetic ratio, and some objects that we're going to look at are going to have a gyromagnetic ratio that is 100 times bigger than other ones. So the fact that there's a proportionality factor here is going to be important to understand which objects are more or less sensitive to magnetic noise. The next term we have is the spin in the z direction. Both the magnetic noise and the signal are proportional to the spin. So we basically have one demand. It cannot be too small. And essentially, so long as it's big enough, the signal to noise ratio is the same. However, when it is too small, we start to suffer from this technical noise. Whatever magical system you can imagine, it will always only be able to measure these spins with some accuracy, with some resolution. So, if this spin in the z direction becomes too small, we're going to start to suffer from just the accuracy or the resolution of our measurement. And there are many different sources for this technical noise source. It doesn't care about what the spins are doing. It doesn't care about any real thing. It is simply how well your detector can measure the physical package, which is the spin. The next term that we have is the axion-like particle mass. Why is it here? Well, the reason is our original equations were essentially a driven harmonic oscillator, okay? And the driving frequency was the mass of the axion-like particle, or the energy to be more generic. But they are not relativistic, so it's very close to the mass. So essentially, the effective force or the effective magnetic field that is applied is oscillating with this frequency, which is why we depend on this mass. And our experiments, the ones I'm going to mention, until now have only been probing stuff lighter than a nano EV, which is very light. But in principle, you can go essentially as high as a milli EV. What determines how high or how low you are is this thing, the resonance frequency. So essentially, this gamma BZ is mostly determined by magnetic coils that we control, okay? We have magnetic coils in our experiment. They can determine how big or small this BZ is. And it is also proportional to the gyromagnetic ratio. That means that things that have a large gyromagnetic ratio are going to have a higher resonance frequency. And when these two things are going to be close to each other, we're going to be unresonant and we're going to be very sensitive to the signal as well as the magnetic noise. When these things are far away from each other, we're going to be less sensitive. What does it mean to be far away? We need to compare them to the decoherence rate or the stabilization rate. And here there are some subtleties I'm neglecting because the decoherence rate is actually a very, very complicated object. It determines essentially how wide is the response of the system, right? If these two guys are exactly equal, that's great. But once they start to stray away a few gammas, that's when you start to lose your sensitivity. This response starts to become lower. And this decoherence rate can change drastically. I wrote here 10 orders of magnitude, but honestly it can be even more. Depending on your system, this thing can be, whatever it is. Most of the systems I'm going to talk about are stuff that's like hertzes, kilohertzes, but again, there are exceptions. Now, there are subtleties about whether a small decoherence rate is always better, because it would always increase the sensitivity. Okay, there are actual reasons to want it to be not too small, related to essentially our actual experiment. One of them was near a train track. Whenever the train passed, the whole experiment would go shake, 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 and it would take the decoherence rate for it to relax. Now, if you have a very short, if you have a large decoherence rate, that means that if you just veto the time, if you just ignore that time where the train was passing by, you can just not care about trains. However, when this thing is small, whatever sudden changes occur, they will affect you throughout your experiment. So that's an actual technical detail that can be quite annoying when you're working with stuff with a very short, with a very small decoherence rate or long relaxation time.
Can I ask a
Yes.
question on this? So it's nice to have physical understanding of these parameters, but is it true that gamma and transverse fields and delta S are all independent? Because I would imagine that when some effect happens, it affects, when a train passes, it would affect gamma, it would affect B transverse, it would also affect.
So long as you're working in a linear regime where you're not actually, I would say, changing the fundamentals of the system, which can happen, like if you're actually shaking the laser beams so they are no longer pointing in the same direction, that would actually affect other things here. But as long as you're working in linear regime where small changes are occurring, usually these things are independent. There are scenarios when they're not, but I think really for the most part they are independent. There is one place, I guess, that we're going to mention a bit later where the magnetic field actually affects the decoherence rate, but you can mostly think of them as independent, at least locally. So, like, if you make small changes in each of them, you can ignore changes in the other ones.
But for example, if you have like sort of inhomogeneous magnetic fields in your sample, then that's going to affect gamma, and it's going to affect B perpendicular, and it's going to affect your projection noise.
The projection noise I'm less sure about. Maybe you're right. I don't see it immediately. But you are right that there are effects that affect multiple of these guys at the same time. That is certainly correct. But I mean, I guess you're right. But for the most part, it makes sense to think about them independently. But you're right. There are effects that affect multiple of them, and that's why building a system can be very hard. You need to run simulations to actually predict these effects from a specific kind of temperature and whatnot. But you're entirely right. So, what are the actual ingredients we have? So, if we want to build our own magnetometer, first we need a physical housing cell. Okay, so this would be, in our case, a glass cell. It doesn't really have to be glass, but you just need something to put them in. The next thing we would have is alkali vapor. We're going to talk a bit more about why it's alkali. But essentially, alkali metals are atoms, with a single electron in their outermost shell. And that electron is going to be what dominates essentially their effective spin. Then you have also noble gases. Noble gases have all their electrons sorted out, in opposite direction. Therefore, you can think of them as just their nuclei. And I like to say this is a logarithmic plot. There's around 10 to the 7 as many noble gas atoms for each alkali one, because the noble gas has so little chemical interactions. You can just cram it inside your glass cell until the glass cell explodes, essentially. In some cases, there are cases where it just explodes independently. But the alkali metals, once you put too many of them, they start to chemically interact, destroy the cell, destroy each other, do bad things. So that's why you can't put too many of them in the same place. And I want to say, I kind of said it, but essentially, when I think of alkali metal, what I should think about is the electron in their outermost shell, from the point of view of the BSM, of the dark matter. It would be the electron which dominates their spin. That's how you can think of them, as tiny floating electrons. While when I think of the noble gases, I should think of them as nucleons, the nucleons inside, because that is what dominates their spin. Now, there's also lasers. The lasers are what creates my pumping term. I'm only actually directly interacting with the alkali metals. They are what's going to get essentially a preferred direction, but they will then collide with the nuclei and make them also have a preferred direction. So there's a kind of a, imparting to the alkali, which imparts on the nucleons. And there's also a probing. That is what actually measures things. And because of simply, electronic energy levels, we are, again, only measuring actually the alkali, and whatever we learn about the nuclear magnetometer, about the nuclei, is coming from measuring the alkali. We do not have an independent measurement of the nuclei and the electrons. So, there's a bunch of other stuff that are less important, like an oven. As I said, this is technically alkali vapor, not gas, so by controlling the temperature, I can control the density. There's magnetic shields, otherwise you suffer from the Earth's magnetic field, so you want to be in a somewhat quiet environment, you put the whole thing inside a magnetic shield. There's magnetic coils, they allow me to control the exact magnetic field that these guys are going to feel. And there's a bunch of optical components that are really only important if you actually want to build your own. I'm happy to explain them to those who want to do that, but not for this talk. So, the one thing I want to put a fine point on is this alkali noble spin exchange. These guys are going to hit each other every once in a while, just because I put them in the same place. That's what makes this a co-magnetometer. This happens very rapidly. And every time they hit each other, they apply a magnetic field on one another. This is a quantum effect, in the sense that you need to know the wave function, you need to do some quantum calculation to actually compute what is the magnetic field that they would apply on one another. And the magnetic field that the alkali is feeling is proportional to the noble gas, and vice versa. The noble gas is feeling a magnetic field that is proportional to the alkali. Because this thing is very rapid, you can just think of it as if they are applying a constant magnetic field on one another. Magnetic field on one another that is proportional to their direction. So, that is our setup, that is our system, and this was what I promised you. I will tell you about action-like particles and spin-based co-magnetometry. Yes?
So is the pumping laser circularly polarized?
Indeed.
That's why you can pump.
Exactly. And the probe laser is linearly polarized, and Faraday rotation is the name of the effect that makes you be sensitive to the spin of the alkali. So the axion-like particles are generating a magnetic-like field, and that can be measured by spin-based magnetometers. And now we're going to talk about established magnetometry techniques. This is things that we didn't invent, but we just realized, oh, we can use this in order to look for dark matter, and no one realized that before. Or at least they didn't publish a paper about it. So, the first thing we want to talk about is compensation point co-magnetometer. This is a work from 2020. It was put on the archive in 2019, which is why the plot I showed you was from that period of time, because that's when we were looking at it and wondering whether we can do better. So, to understand what a compensation point co-magnetometer is, we need to look at the response of our detectors to noise. Okay, I don't care about the signal right now. All I care about is how much is it going to react to noise. And I remind you, this was our beautiful equation. We showed it earlier. We're going to show it again. And again, I'm not caring about the signal at all. The only thing I care about is what is this magnetic field that the alkali is feeling right now. And as I told you, it comes from the noise as well as the effect on the noble spin on the alkali. Okay? So the noble spin, when they meet each other, they apply on each other a magnetic field. And you can forget the exact prefactor. In the end, the important thing is that we're measuring the noise as well as something times the noble spin. And what about the noble spin? Well, it has a very similar equation. We're going to ignore some back reaction effects. They are important if you actually want to do the details correctly, but they are not super important for right now. And what we're going to do is we're going to see what happens when I slightly change my slightly change my magnetic noise amplitude, and I'm measuring the alkali. Okay? What we want is to not be sensitive to noise, right? So I want that if I change the magnetic noise, I'm not changing the spin of the alkali, which is what I directly measure. So there's this prefactor that I put in gray, which means you don't need to think about it too hard. And then there's the one here. This is exactly this thing. It is the direct effect of magnetic noise on the alkali metal. But there's also this object. This object is what the alkali sees from the noise when it measures the noble gas. Now, this expression is kind of ugly. You don't need to worry about it too much, because we're going to kill two of the parts here, which is the mass of the axon and the gamma noble. If you take that, we're looking at very small frequencies, NA goes to 0, and also very narrow gamma noble, this thing goes to 0, then all you have is essentially some prefactor divided by the magnetic field of the noble. And this thing I told you, I can control with magnetic coils. I can change how big is essentially the response of the noble gas to a regular old magnetic field. And by choosing the right numbers, I can essentially make that this is 1 plus minus 1. And essentially this whole thing is 0. So that means that when you're looking at low frequencies, the compensation point is where the noble gas is always cancelling the magnetic field for the alkali. The alkali will never know about the magnetic field, only the noble, well, no, in the colloquial sense. It doesn't know anything. It's an atom. So it wouldn't know about the magnetic noise. It will only learn about actual signal. And this is what is defined as the compensation point. We are not the people to invent it. I'm going to give them credit in a moment. And at low frequencies, this means you can be completely insensitive to noise, and that's great because low frequencies is also where noise can tend to be very, very big. And there's another effect that the two species are near resonance, and that means that you can be near train tracks and still do your measurements rather than worry about waiting an hour after every time something bad happens to your system. But this part is less important and more complicated, which is why I'm not going to talk about it too much. And we're, as I said a moment ago, not the people who invented this. This compensation point co-magnetometer was invented by the O'Malley's group from Princeton, and this is data from 3 of his students. Georgia Vasilakis is the purple one, the green and orange are by Justin Brown, and the blue is his first student, Thomas Kordak, who I believe is also on that first paper that invented this co-magnetometer. And what you're looking at here is the magnetic spectral density noise, what square root of it, doesn't really matter. You can just think of it as the effective noise that the detector is measuring, and they took data for their own, happy whatever reasons, and they published that data. And we can just look at this data and say, oh, if I had an axion, then this point right here would have had a giant peak coming from the axion. It would have looked like a coherent field and would have drastically increased the noise. And because they didn't see that, we know that there's no axions here and here and here, etc. And this is what allowed us to create constraints just using that data. And first we just put constraints on the coupling of axions to electron. And as you can see, maybe it's not super happy. We only improved by like an order of magnitude, which is good maybe, but not too good. And the reason is that the response of the co-magnetometer to anomalous fields that interact with electrons is much reduced. However, things are much happier when we look at the results on neutrons. So, this is the results we had. As you can see, we are almost reaching the current best astrophysical constraints. And this is simply because this detector is extremely sensitive and is exactly able to remove magnetic noise, which is the thing that these spin-based sensors are going to be most bothered by if you want to look for new physics. They would be sensitive to this magnetic noise. However, there's an important detail that you can't see, which is that the smoothness of this thing, it's even not the one dominated by the projector and level of plotting, but in general there's a smoothness here that is not actually real. When we look at actual constraints later, you will see that they are very ugly. They have ups and down and ups and down. And the reason is that essentially we can the data that we had was public data that wasn't essentially the full noise spectrum. The actual constraints is only on a specific set of frequencies in this plot, while it could be in theory that the axion was hiding somewhere in between these points. However, there's a recent work by Lee et al., also from Princeton, that actually had access to the full raw data, and they were indeed able to cast constraints that are very similar to those, slightly better, because, as we also mentioned in this work, without the full data, there's really only so much we could do. But this shows you that already with existing techniques, with real data that is just out there, you can get amazing results. And there are several lessons we can learn. The first one is indeed that there's a huge potential, just with existing data, things that people have already done 10 years ago, that you can use to improve drastically the current parameter space constraints on axion-like particles. The next thing is that electrons are very hard. Essentially, they have a very wide bandwidth that reduces their response compared to technical noise, and they also have a very large response to background magnetic field that makes them very hard to work with, and therefore we're not going to talk about electrons for a while until the end of the talk. And finally, we didn't have data, and that was very sad and really limited what we could do, and that's why we need our own experiment. And that's why we started the Noble and Alkali spin detectors for ultralight coherent dark matter, or NASDUCK for short. I keep changing the logo. Since we're not a brand, we don't really have to commit to one, but at some point we probably should. That's our current logo by me. We have 2 publications, which I'm going to discuss, as well as several works in progress. And now that we are, armed with our knowledge of spin-based magnetometry, we're only going to need to understand essentially the problem, and then I'm going to briefly explain how we solve them and show you the results of these detectors. So, these are the existing and upcoming experiments of NASDUCK. There's NASDUCK Bloch, which was our first result, NASDUCK Surf, NASDUCK Modulated, and NASDUCK Subtracted. NASDUCK Modulated, admittedly we have prototype data, but it seems like some cables were disconnected during the measurement, and there's a very specific thing we need to make this detector. We need a rotating table. So we probably want to redo this before publication, and until we have access to it, this one might take a while. There's also another thing we're doing that is currently at the theory stages, so I feel like there's only so much you can cram in one talk. So instead, we're going to only talk about these 3 works. NASDUCK Surf. We're going to go asynchronous, because it's a much easier to understand work than NASDUCK Bloch. NASDUCK Bloch, and NASDUCK Subtracted, which is a work in progress. And so, to understand what is the problem with the self-compensating magnetometer, we need to go back to our beautiful equations. And what we're going to do is we're going to forget about numerators. We are only looking at denominators right now. And what I want to mention here is that as we increase this mass, we increase the mass of the axion, we're looking at higher and higher frequencies. The signal response, you can forget about this object, that object, that object, that object. It's going to go like 1 over the mass squared. You're losing sensitivity as you're trying to measure higher and higher frequencies of axions. And that's bad, because you don't want to lose sensitivity, you want to have a very nice sensitivity. And essentially, the way to resolve this is very simple. I told you we can control these magnetic fields, so all we need to do is essentially tune the magnetic fields here, so we are always on resonance, at least for the alkali. And the improvement factor is going to be essentially the 1 over ma that we lost earlier, so now we're going to get ma, and divided by the width of the alkali. So this is how we're going to gain, essentially. This is the simplest thing you can imagine, just change the resonance frequency and measure on resonance rather than off resonance. That's a very simple thing. And this is what leads us to NASDUCK surf. This was our latest publication, and we're going to briefly explain what surf means. Don't want to go too much into details about it. It just felt really bad to mention the word surf and not actually say what it means. What it actually means is spin exchange relaxation free, and it's a very complicated thing, but essentially the smaller this gamma alkali, the better the thing is going to go. The actual parametrics are not super important, but I really need to stop playing with this. But essentially, if you can make a more narrow detector, you can get better results. And the alkali metals, despite my biggest of wishes, actually have nuclear spins. They are not just floating little electrons. And therefore, they have hyperfine levels. They have splitting dominated by the nuclear spin. And you can think of these hyperfine levels as A and B. They have distinct frequencies. And essentially, whenever two alkali metals collide with each other, they're going to flip between A and B. And this is going to create this ugly little plot that you have the spin of the phase, of a spin that rotates with one frequency, and then it hits another spin, going to rotate with a different frequency, hits another spin, rotate with another frequency, and you're essentially losing coherence due to the spin exchange collisions. However, the spin exchange relaxation free is when these collisions are going to be super duper often, so you're increasing the heat, increasing the density, they're colliding all the time, or you're reducing the magnetic fields, you're going to essentially sit in an effective single hybridized level, and that is why spin exchange no longer induces relaxation, so this is why it's called surf. Again, this part is not really important, it just felt, morally wrong to not even mention what the word means in the title of the paper.
Can you comment on the time scale in the last plot?
Yes, so it strongly depends. Honestly, we are not going the full surf. At the full surf, I guess you can go as well as hertzes, so the relaxation rate becomes hertzes, while the spin exchange rate is like tens of kilohertzes. We're getting 100 of hertzes, so we're getting 2 orders of magnitude. There's 2 more to get, but because
something has to be driving your system at that lower frequency, right? Or is that just the beat? No.
That is induced by the magnetic field. This omega A and omega B are proportional to the magnetic field.
Yes, but in the last plot there is a characteristic frequency. So the frequency of little wiggles is the omega A, omega B.
It is essentially a weighted sum of omega A and omega B. It is a specific sum related to how much time they occupy A and how much time they occupy B related to their spin temperature.
Okay.
So this was our results from the NASDUCK surf. There's a little fun fact. So we also put bounds on axion-proton interaction from the fact that the alkali have a nuclear spin. And strictly speaking, there was no previous constraint in this specific range between 10 to the minus 2 inverse GeV to 10 to the minus 3. Admittedly, I cannot think of a single model where you would have such a giant interaction with protons, no interaction with neutrons, or you could even produce dark matter. Like, this is a very weird model that no one thought ever existed, but it's nice to actually exclude it officially. On the axion neutron case, things are, I would say, a bit closer. We are only around 2 orders of magnitude worse than the current astrophysical constraints, and you can still improve. There's still ways to use, standard systems not working too hard. They can give you another extra order of magnitude. You can already see this blue little line, NASDUCK okay, and that's because, as I told you, I didn't go chronological. So at this point, we already had the results of the NASDUCK okay experiment. Yes.
Curious, on this plot, is there like a target anywhere on the y-axis? Or
the target is below. We're going to reach targets when we're going to look at the next plot, but even there, the real targets are still quite far, but they are there. They are not going to the QCD line, honestly. There are 2 main production mechanisms that I think are more interesting than the QCD axion, which are misalignment production, which, even though you're talking misalignment, actually you don't need to be doing the QCD stuff. But the other one is, I forgot the name, is it kination or fragmentation? There's 2 ones, I confuse them, which are a bit easier to reach. We are, I think, around 4 orders of magnitude above them, but the fundamental sensitivity of these detectors is not actually where we are currently. There are places to actually improve, though when I talk about trying to reach targets, we're going to try to go a completely different route. It's going to be at the last part of the talk. So, the NASDUCK Floquet was our first work. I don't really have a good logo because Floquet is kind of an abstract thing. It's a rotating fit in the z direction. I don't know how to invent a logo for that. But this was our first publication, and to understand it, we need to go back to our response. So we had this very nice equation, and we can of course note that this thing is coming from the alkali response. This thing is coming from the noble response because we're measuring the noble gas through the alkali, through the lasers. So there's 2 parts here, the alkali and the noble, and we need them both essentially to be on resonant. However, we can look at the ratio between their two resonance frequencies. So this is simply this divided by that. And their magnetic field that they are each feeling is essentially, just the gyromagnetic, there's the gyromagnetic times the magnetic field that I am inducing, the one by my nice coil, plus some constant related to how much they affect each other and whatnot. And if I take a large enough magnetic field, I can forget about this constant, and essentially I get that the two resonance frequencies have a ratio which is the ratio of the gyromagnetic ratios. And that can be a giant number. It is indeed around a few hundred. So that means that whenever the alkali is on resonant, my noble gas is very, very off resonant. I cannot have them both on resonant once I want to measure high frequencies. And that's not good, because again, when I'm off resonant, I'm starting to lose sensitivity, become sensitive to technical noise. So, this is what the NASDUCK Floquet experiment was meant to solve. And I'm going to tell you a bit about Floquet fields. First, we're going to have a math slide, then we're going to have a more fun illustration slide. This is what a Floquet is. It is essentially modulating your field in the z direction. And if this was our previous solution, it is now going to become a mess, which is this expression. It is essentially, forget about the full details, essentially you are modulating your response by the Floquet frequency and all of its harmonics. So if I had a signal at 5 kilohertz, I'm going to see a response at 5 kilohertz. I'm now actually going to see a train of responses. I'm going to see a response at that frequency as well as all of the harmonics away from it of the Floquet frequency. And it also modulates the resonance frequency of the system. These are two actual sums. These are not, you don't have to have n1 equal to n2, but this is what it essentially does. This is the math, and we believe in math. If you plug in simply that you take the Floquet frequency to be exactly the difference between the two resonance frequencies, then you simply get, in one specific harmonics, the one of 1-1 essentially, that the alkali metal is responding with the Floquet frequency, with the noble gas's resonance frequency, right? Because I shifted it by the difference between the two. And it is measured still at the very high frequency that is determined by the sum of these two guys. So this is very useful because it allows us to put these two guys with a resonant simultaneous response. And this is, again, a bit of a more math slide, but if we want to understand what it actually looks like, I have some plots which are not to scale. So this is the response of the noble gas here in black, and this is the response of the alkali metal, and this is much bigger, the frequency here is much bigger than the one here. We always measure essentially the response of the alkali times the response of the noble, because we are measuring through the alkali the noble gas. So, if my signal is sitting right here at the frequency of the noble, because my alkali is off resonant, I'm going to suck at being sensitive to it. However, if I introduce a Floquet field, which is exactly the difference between these two guys, then now the alkali has a response not only here, but also here and here and here, etc. And that means that when I'm now measuring the alkali metal, I can still get an on-resonant response despite the fact that it is at a different resonance frequency. So this is what a Floquet field does, and it gave us a very nice result. As you can see, I warned you that these lines tend to be very wobbly, and in fact this is a subsampling of the full thing, because this is a very, very, there's a million statistical tests here that are independent, around a million that are statistically independent, so that's why you get these, jagged lines. And what you're seeing here is that there's a nice projection that is a slightly more advanced system, truly nothing, groundbreaking systems that actually exist. And if they did that, they would be able to reach here. We don't fully know actually why our detector sensitivity dropped here. This is not a fundamental thing. This is just a problem of our own detector. And as you can see, we are already able to, with a slightly more advanced system, really improving the astrophysical constraints, and we are already not that far from them. And that's very nice. And indeed, the target, just to answer your question, I think is sitting around 3 extra orders of magnitude below, which is not too good, but honestly, we went from 10 orders of magnitude to 3 orders of magnitude. I take that as a win in 2 or 3 years. So, one other thing I want to mention is that essentially our sensitivity was limited by the noise of the probe beam. So that's an order of magnitude larger than the fundamental magnetic field noise sensitivity in this system. So really our SZ, I said our main demand, it cannot be tiny, it was tiny. And we lost an order of magnitude for no good reason. And the thing I didn't show you, because these are more updated results, in the last year or two, there have been other collaborations doing similar experiments after our own. At the past, it used to be just us and Casper. But by now, we have shown how we can do this with existing technologies, and there really has been a blooming of, I think, around 4 different collaborations that are doing the same thing. And if one of them has more manpower than the order of 4 people that we have in NASDUCK, they can do this experiment really without working too hard and improve just by an order of magnitude. You don't need any much more advanced system or anything, and already probably beat the astrophysical current constraints, which I think is very nice, somewhat sad, because they will probably be cited rather than us, but we will survive this and science will improve. So, the current summary is, again, we started by saying that axion-like particles create a magnetic-like field that can be measured by spin-based magnetometers. And NASDUCK has opened up new possibilities. There are several now groups that are doing this after around 10 years, a few years where it was only Casper's results. And indeed, they have been able to improve by many orders of magnitude by using similar techniques to ours. And now we're going to talk about how we actually can cross that bound and do new things. Now, just because of the time, I'm going to skip some slides about what else you can do with these, but suffice to say there's a lot of other cool things. These are detectors that were not originally built for dark matter, and you can do many, many different things with them rather than just look for axions. And I'm going to straight up skip to this guy, which is the longitudinal measurement. There's another thing by NASDUCK that I'm not going to have the time to talk about, because this thing is what leads me to, I think, the most interesting project here. So NASDUCK subtracted less important. I want to talk about this thing. So this was a theory paper that we put out last year about using this time detectors to look for scalar dark matter, not axions, okay? Axions, slightly uglier brother, I would say, or sibling. It's not gender. So since coupling constants are scalars, if you want to understand what scalar dark matter does, you can think of it as essentially mimicking the variation in these constants. So every time you see a coupling constant, you can switch it with a scalar field because they have the same properties under Lorentz. And therefore, because the scalar field oscillates according to its mass, you will see a variation in fundamental constants. That's on one of the briefest explanation I can give. And if you have a permanent magnet, it is essentially a magnetic field proportional to the electron charge as well as the mass. And if we look at this beautiful animation, if I am now measuring the magnetic field along the z-axis, along the direction of that magnet, I can now be sensitive to the effect of the scalar dark matter modulating that permanent magnetic field. And there's already an experiment by one of the collaborators that they've already done. I'm pretty sure they have the data already. But essentially, this is really an easy experiment that we just thought, oh, we could do it. It's going to have a nice result. Then we did the theory paper. Maybe not so nice results. But yeah, let's do it. We already have everything ready. So, the reason why I find this still important is that it led me to the question, which is, can you use longitudinal magnetometry to look for axion-like particles? And usually when you ask a question like this, the answer is yes. But actually here the answer is no. At least the naive one. And the reason is very simple. I was very happy to say that we are linear in the coupling constants. That's amazing. That's nice. But the spin in the z direction, if you wait long enough, is actually going to be, it's kind of like, sine of theta versus cosine of theta. It's going to go like the coupling constant squared. This is what happens. This is the polarization in the z direction if you wait a long enough time. Okay, it's going to be proportional to the coupling thing squared times and up to some ugly thing. So that's bad. And this might tell you, let's quit. Why do we need to do it? Let's just think of other ideas. But I want to motivate it slightly. And the way I'm going to motivate it is look at the axion-electron coupling parameter space. This is by Kieran O'Hara's website, the most useful GitHub for dark materialists at the ultralight range, which accumulates all the different proposals people have and all the different things. And as you can see, there's still not that many existing experiments that are looking for this. There's quite a few new ones, but there's still not that many. They're not so close, I would say, to even in their predictions to be beating the astrophysics, let alone reaching interesting targets. And I have a bonus plot. This is a more famous plot, the coupling of axions photons. And the reason why I showed it to you here is a very specific mass range, which is this one, the millieV mass range. Turns out, if you take 10 Tesla field, okay, the highest we can reasonably think with reasonable magnets, and you take an electron spin-based sensor, their gyromagnetic ratio is bigger than the nuclear one, so that's why they have higher response, you will be sitting right at the millieV. So, there's a motivation to try to maybe think a bit more carefully what we can do looking at axions in the presence of giant magnets. And when you think about it a bit more, you need to remember something called the spin shot noise. What is a spin shot noise? Essentially, if you have zero temperature, you have a constant magnetic field, you're going to have thermal polarization that is 100%. All my spins are going to just be pointing towards that magnetic field. This is without axions. And because the spin in the x direction is not commutative with the Hamiltonian, whenever people measure the spin in the x direction, they are inducing a quantum noise that is limiting how much we actually believe we could be able to ever reach the QCD axiom. That is a fundamental limitation of these kinds of measurements that makes it very, very hard to believe that they can ever reach the QCD line at the ultralight masses. And the magnetic noise is essentially going to be going like the square root of the number of spins, because I don't know, that's how quantum collapse works or whatnot. And you can think of this as essentially taking the signal and dividing it by the square root of the number of spins. So that means that the more spins you have, the less this quantum noise is going to be important, which is why when you put projections, you can somewhat forget about it because you say, oh, I will take a meter cube giant detector and it'll be fine. However, when you measure in the z direction, which is what we do in the longitudinal case, this does not exist. The system is sitting at its ground state, is sitting at an eigenstate of the Hamiltonian, so it doesn't matter how much time I measure it, I'm not going to induce a quantum noise when I do that. I'm measuring an eigenstate, that means that I'm not sensitive to noise. And in fact, you can think of this spin short noise as an observable, because when an axion is doing its thing and making the spins tilt, when we measure a spin in the z direction, now we are inducing a spin shock noise, because the spins are no longer polarized in the z direction because of the axiom. And whenever we measure them, we are in fact going to get a signal that is again linear in the coupling constant. And there are several other interesting features. For example, usually you go like 1 over the bandwidth. Here we're going like 1 over the square root of the bandwidth. So that's a very weird thing. And you also depend on the longitudinal relaxation time, which I didn't mention at all. It's one of the details I said, like to leading order and relevance in the Bloch equations. There's actually 2 relaxation rates, one in the direction of the magnetic field, one in the direction perpendicular, and this number can be much smaller than gamma 2. So you can actually get a giant enhancement here because you are dependent on this longitudinal rate that usually doesn't really matter for anything. However, of course, you need to remember that this thing is suppressed by the square root of the number of spins. So if you take here 10 to the 20 spins, that's going to be 10 orders of magnitude suppression, which, is quite bad, I would say. But usually you want this thing to be big, but now that there's no longer a spin projection noise, and in fact your effective signal goes like 1 over the square root of spins, you might want to actually make the system smaller. So this is a very unusual kind of parametrics that might change completely how you want to think about it. And this is just a very interesting idea. There's a lot of interesting notes that I'm not going to really cover all of them, but we're right at the end, so don't worry too much. This thing can actually be you can add another spin-based amplifier because there's no back reaction here. The system does not respond at the frequency at which you are measuring. So that's a very interesting detail that usually does not exist. There's also some interesting quantum things that honestly, I'm not sure enough that they are actually useful in any way. Because if you measure essentially a derivative of the magnetic fields, it turns out that in the quantum way, it's not just like measuring, cosine. The derivative of cosine is going to be omega times the cosine. You're actually going to be measuring stuff that, decays with rates of gamma. So there's going to be some non-trivialities in the parametrics that could drastically enhance the signal, but also possibly the noise. But as far as I can tell, no one has ever thought about this thing. So I think it's just a cool effect that, not everything has to be particle physics necessarily. It's going to be nice to learn about. And there's also a bunch of other, interesting things. But the main one is that there are many challenges for this to actually ever be implemented. This is still at the theory stages. But there's also many interesting possibilities. And I think just by itself, this is a very interesting kind of detector that really, beyond dark matter, no one seems to have ever tried to use quantum noise as an actual observable. So, to conclude, the use of spin-based sensors to look for dark matter has really bloomed and expanded in the last few years. I originally wrote here 5, but if you took 5, that goes all the way to the first few Casper results. But I would say in the last 2 years, really, there has been 3 different papers by, there have been 5 different papers by 3 different collaborations. So really, there has been a huge expansion in just the last few years. And existing technologies, which is what essentially I think almost everyone has used until now, using well-known technologies of the metrology world, of the world of very accurate quantum sensors, can have amazing capabilities and already can enhance what we already have done, using whatever we had lying around. But if you really want to be doing interesting things, you got to be more creative and you got to think of new ideas. And there are really, I think, many interesting possibilities to explore and many promising directions. And finally, the original name I wanted for this detector would have been a dark matter experiment. I was told this is too ridiculous to actually name your detector that way, so instead we made it more formal by going to business school, make it into NASDUCK. Thank you very much for listening.
Yeah, so I don't really get what you're saying when you go to the noise part. Are you still using the same system? And
so what happens here is essentially,
I think he's asking, is it the same kind of system? Like what system?
So the actual system that we would need has the same basic principles. However, until now we're working with alkali vapor. This would require an alkali, sorry, not an alkali, a solid essentially, because you want to increase the density. Okay. So the basics of the system are kind of the same. They're still floating electrons. However, now they are no longer floating. They are trapped inside a lattice. But this is more because of technical details. This equation, you can use the exact equation I showed you earlier. If you solve them also for the spin in the z direction, this would be the answer. I didn't really change that. But that equation was fully classical, okay? Well, okay, I guess spins are inherently quantum, but it was classical in the sense that it was ignoring the self-correlations of the spins. And to actually see the signal, you would need to actually do a more complicated quantum calculation, which we did, using density matrices, and that's how you usually calculate the spin projection noise. So the building blocks are the same. The practical system is going to look completely different. It's going to be a cryogenically cooled system with a 10 Tesla magnet. But if you forget about all the actual details, if you just look at the math is kind of the same. Until you actually need to compute anything quantum. But I guess the Hamiltonians are the same, which is something. Is that clear or not yet?
And are you still measuring the perpendicular polarization?
No, so now the longitudinal measurements are measuring the longitudinal polarization, so not the transverse, and that's why you suffer, essentially, naively, this b squared, because the transverse one are always going to be linear. This one is naively going to go like the second power until you do the quantum stuff. So you're no longer measuring the perpendicular, no, you're not measuring, you're putting your detector along the same direction as a giant B field, which is why you actually need a radiometer to remove that background magnetic field. You have to kind of subtract that.
And why do you need the high density? Because I thought you need to lower the ends.
So that's why I said that the parametrics are actually a bit complicated, and the reason is because the actual sensitivity of a magnetometer that you're going to use to measure this thing can also drop when the thing is smaller and smaller. So that really depends on the actual implementation that one would apply. However, usually there's a hidden factor if you're not doing an optical measurement. This, how I said that here, the actual spin projection noise go like the square root. However, it is the signal divided by the square root. If you're measuring in most direct ways, it would just mean that essentially you're losing 1 over the square root of the spins compared to the usual strategies, but you are still actually proportional to the square root of the number of spins. So there's a lot of subtleties here.
So for your longitudinal measurement, the next slide I think, for this one, this square root PST is just a signal.
So that's why I did the little dashed line. The reason is it depends on how you actually measure this thing. If you were to now...
This is just the signal of the axion. What happens to the noise? So do you have SNR for this?
So the answer is it strongly depends on what is the actual parametrics here, knowing what the noise would be. It is, as you go to the EMF stuff, for example, you would need to essentially have a highly stable readout, because as soon as you slightly tilt, you would measure again spin projection noise, because you're no longer measuring in the same direction. If you're measuring directly, the actual noise is simply going to be what I called earlier the readout noise, or the noise of the squid, which is whatever 10 to the minus 16 Tesla per square hertz. It's some specific number.
Well, but the squid gradiometer noise in a direction in which you don't have a background field versus in a direction in which you're applying BZ is completely different.
So there's a baseline, you're right, but the actual magnetic field in the frequencies at which we care about is 0. It is only the DC part that is going to be gigantic. But there are also other readout methods that you could think of. For example, you could put essentially the whole thing, there are tiny, I forgot the name. There's a name for structures that have a large magnetic field in the very centered point. Because this thing can be very small, essentially you could put it there. And then you can put your detector, your actual detector right outside of it. And then the parametrics would again be different. You could imagine having a spin-based sensor also sitting on the outside. Or you could have essentially that, again, something that is not a squid, but instead an actual additional spin-based amplifier, kind of like Casper, if you're familiar, like using a ton of xenon, of polarized xenon to measure this effect. There are several possibilities. This is, like I said, a work in progress. Currently, we're trying to understand the fundamentals of this thing. Whether or not we can actually think of an easy experiment to look for, unclear yet. But it seems like, again, this has completely different parametrics than the usual. And, if you're being what I call the fantasy football case, where you're kind of choosing your favorites of this paper and that paper, choosing all the best kind of ideas, and you're putting them together, not caring really about whether they actually like to be smushed together, it seems like you can actually get to the QCD line. But practical, limitations tend to forbid taking all your favorite little papers, all the results of all of them, essentially. So again, before we actually know, before we need to actually finalize to see what is the actual best implementation we can think of. But as far as I can tell, no one has thought of something even remotely close. So it's possible that once we put it out, someone smarter than us will come up with a new implementation that would actually improve drastically compared to what we were able to think about.
And can you also, like your DC versus AC thing actually reminded me, I wanted to ask you, so on your plots you also had frequency on the limit plots. Is that actually the frequency of the measurement, not this one, the surf measurement?
Yeah, it is.
So you're measuring from like 1 hertz to kilohertz or something?
Yeah, so the surf stuff,
Are higher. Okay.
yeah, it was a bit higher frequencies. The Floquet stuff was a bit lower frequencies. In principle, you could also do the Floquet stuff at higher frequencies. It was just what we decided.
But so the Floquet is the difference, right? So is that where your magnetometer actually operates, or is it the magnetometer is operating at some higher frequency and you down convert to this frequency? That's really
so for the Floquet, what really happens is that this is the sensitivity. Sorry, this is the frequency of the noble gas response. The alkali metal was setting a much higher frequencies, at tens of kilohertz essentially, and that was what we were actually reading out. However, again, the actual signal frequency was sitting here as well as the response of the nucleus, but when we read it out through the alkali, we read it at much higher frequencies. Except in this tiny range here, but that's beside the point. There we did some deciding effect.
Other questions?
Speaker again?